Bilek, who is going to talk about the limitations of AI.
Thank you for joining me today. As Rick said, I'm Seb, and I'm hoping to shed some light on some of the difficulties with AI that most people might not be thinking about, just like interacting with APIs and developing these systems, but not really thinking about some of the deeper examples or more technical examples, which I'll start off with, where AI isn't actually as easy as just like attaching some neurons to a problem and making it work. So yes, I'm going to be talking about two categories of these limitations, one being the technical aspects where you're working very low level with deep learning and you're just having to train it quite a narrow AI really, and then I'll move on to like artificial general intelligence problems relating to misalignment, which is quite popular with ChatGPT and things. So the first thing we have is fitting, and we'll start with overfitting. So when you have some sort of task for ChatGPT, let's say we have some relationship between X and Y, we have some samples of that data. So like these blue samples over here, and the true function might be that orange line. And obviously we want our model to imitate that as well as possible. So ideally a good fit is where your model is that blue line and it's sort of imitating the general concept of the relationship between your data. And maybe it might have some systematic error where your samples have drifted a bit, or random error just because of the instruments that you're using. And this is quite a simple example, but it's probably the easiest way to show it off. So obviously this is a good fit, but once you start scaling or making models a bit bigger, you'll actually find that they don't necessarily become smarter like instantaneously. What you'll find is, depends what data obviously you're using, they can start memorizing data points where during training they actually perform better. So you're trying out these samples and you're like, yeah, it's getting the samples much more accurately. But then once you've tested it, once you check like, okay, what if X is over here, and it gives you this Y that is like way off, and then you know that it's been trained badly. And this is sort of happens because the neural network is too large to some extent, and you can solve it just by shrinking it a bit. That allows it to have that good fit where it generalizes the information more. Or another option could be to just have better data that follows that line better, otherwise obviously it does that stuff. And this can scale to larger models, obviously, like ChatGPT. You might not see it that obviously, but issues with ChatGPT can arise from these technical issues, but obviously OpenAI are pretty smart and they've got a lot of it under control. This brings us to overfitting's opposite, which is underfitting, and that's when your neural network actually doesn't have enough neurons to comprehend what sort of function you're talking about. So it just goes for like a really rough estimate. It's like, okay, I have no idea what this function is. I guess these samples are going in that direction. And as I said before, this is quite an oversimplification, but it's still possible. It's still possible in lower level applications. Like that's like a sine wave. So if you try to teach a neural network to imitate a sine wave, this could actually happen depending on the size of the model, obviously. And that's why you just change the size. So it has a solution. It's not as like less solvable, like misalignment, which is sort of a new phenomenon. Next we have vanishing and exploding gradients. This is a little bit more of a complicated issue, but it relates to recurrent neural networks, which are neural networks that process dynamic size data, like music composition or text. Neural networks are a bit like this cable with these sort of wires, and you can only trigger certain or power some of the wires at the beginning of the cable, and then the same wires at the end are powered, but you can't really send more data than that through the wire, so you send it over time. So with the recurrent neural network, you just send, your text or your music composition through the neural network multiple times. And in between this sort of bit, it actually also sends off a little bit of context to the next iteration, because if you start using some word and then for no reason you chuck into the model a different word, it has no idea like why you're giving that word. The only way it would have that idea is through this context layer, where it sort of becomes this several neural networks stacked on top of each other, and that's where you do the deep learning. Unfortunately, this isn't foolproof, because you have this exact problem where the relationship between these neurons and the calculations for the gradient is they're related through the chain rule, which is like a calculus calculation, and that sort of calculates these nodes through a product of gradients, meaning that the gradients multiply over time, specifically this node layer. And that's basically like indexing your gradient, so to the power of 100, and any number to the power of like 100 starts exploding or vanishing. So let's say you take 0.9 to the power of 100, it just becomes a lot lower than, I mean, you should be expecting that, but it's not ideal, obviously, in machine learning. Or if you take 1.1 and go to the power of 100, it will still become quite a significant number. So the solution for these is, for the current neural network, usually you just have this one node that, sends off a neuron, which just sends off information to the output, and then also sends off a bit of information to the next iteration as like context. But some smart people invented the LSTM, so long short-term memory cell, and I'm not really sure how that works, but it mitigates the effects of this this issue. It isn't foolproof though. It does stop working after, and I think the efficiency of training the neural network does go down a little once you're using these cells like the GRU and stuff. And then obviously we have transformers, which are in no way, shape or form recurrent. They just sort of like pick out relevant words in your text, and then that's what they put into the neural network. But it's not the neural network processing each one of your words like for each iteration. It rather processes all of your words at once using these attention layers, and then reacts to that using those tokens. Well, and our last technical issue would be local minima, and that occurs when your model, any deviation from its parameters, let's say has a single neuron for some reason, you have the bias is this sort of x-axis, and your y-axis is the result or the actual loss and reward of the model. And any deviation or small deviation in that bias value would cause it to perform worse. So actually that backpropagation or stochastic gradient descent moves up a bit, but that would do worse. So it moves back into this local optima, and it doesn't actually advance as much. It's obviously an issue. It's a bit like a person working in a job that they don't really actually like. And then for them to find that global optimum, they have to go around and try a bunch of other jobs before they can find a job that they actually like. But that's a bit more complicated with these technical issues where you have these models. The solutions are a little bit different, and this is also to show that it's more complicated than just a 2D graph. You can have this 2D plane of possible results for the number of dimensions in this plane. So an n-dimensional plane where n is equal to the number of parameters in the model, because for every parameter has an effect on the results. So you can't exactly imagine it this way, but it's a good enough representation. And yeah, so the idea is that you have a few solutions, one of which is using a optimization function with a bit of momentum, so that when it scales these this n-dimensional plane, it can sort of overcome plateaus, and maybe even overcome some peaks, but that isn't exactly the best way to do it is like to do a mix of things, including increasing the learning rate, and increasing the learning rate of the model sort of makes the movements across this plane a lot more aggressive. So it sort of shoots over to different places, which it's ideal when the model is in the first stages of training, but once it's starting to get efficient at its job, you want to start decreasing that learning rate, which is what people do. They have like a learning rate that decreases slowly. Another option is how you batch your data. So data that would be batched in very small batches would mean that like the results from each batch are a lot more random. However, if you have bigger batches, they're more sort of they're more general and more averaged out, the results of your model. And so yeah, you sort of want to mix them around. You might maybe start with smaller batches so that experiments a bit more, or you might use smaller batches when you feel like it's stuck in a local minima, and then when you want it to start like fine-tuning that process, when you actually want it to finish off its learning, you might start using larger batches just so that it descends the gradient at a more general and average sort of ways. Yeah. And of course, you also have transfer learning, which allows for a more understandable approach of teaching the model, where you can teach it some simple things like ChatGPT. They didn't go straight to text response. Something simpler where you have a lot more data, like text completion or maybe translation and other things, and slowly they give it things and they build up that that learning so that they have much more control over that process. Now we're getting to the fun part, because this is misalignment, and misalignment means trying to align the AI model with our attitudes, values, and beliefs, trying to actually get it to understand that, which sounds a bit like simple in a way, but it's definitely not. Like, maybe to some people it doesn't sound simple, but the point is it's a very complicated, and it has a lot of twists and turns. It's a complicated process to understand, especially when we start thinking about it in a very extreme sense, where this general intelligence might be a lot more capable. Like, how do you define exactly what you want it to do, and how do you stop it from finding these loopholes? And what if it's no longer actually trying to imitate humans? It's not narrating, but it's actually sentient. What could be going wrong? What could be going on? So for that, I'll be using the AI stop button analogy. Is a very popular thought experiment to sort of think about this misalignment concept. So this is Midjourney sort of failing to draw a vase and a robot with a stop button, but I just put a vase there, and it doesn't really need images. It's more of a thought experiment, but there you go. So in this thought experiment, you have a robot with a stop button, and the idea is that if you press the stop button, the robot will completely halt any sort of procedure that it's doing. And this is your robot, right? It's an AGI, it's general, it'll do exactly anything you tell it to do. So in this scenario, you said, I will give you a reward of 100 if you bring me back a cup of tea that is warm, and somehow you're able to specify that. You can specify that, and it starts thinking, it makes a plan, it sees the kettle, it starts moving forward, but then, oh no, you forgot your priceless vase with your grandmother's ashes, or a very old artifact, or your little baby on the ground for some reason. And it starts moving forward, but it doesn't stop, because why would it? Like, it's in the way of it making tea. It wants you to make, you want it to make tea, so it's like, oh yeah, sure, I'll just step on the baby or something. It doesn't care. So you go over to press the stop button, but well, you should have expected it, but let's say you didn't, is that it tries to stop you, right? like, it's trying to make you tea, and you pressing the stop button won't help that. So it's actually stopping you pressing the stop button, and that's sort of something obvious that you should have thought of, because it's trying to stop you from ending its existence in a way, because it was trained to exist. It was trained to complete the task you wanted to do. So yeah, assuming that you haven't learned from this issue and haven't actually thought about it theoretically, which is why we're thinking about it theoretically and are actually doing it right now, you might move on and say that, okay, well, let's assign the same reward to the stop button as it making me a cup of tea. And here's another great PowerPoint illustration with Midjourney, which I also failed the stop button and couldn't press the stop button because there wasn't one. So yeah, so you say, okay, so stop button is the same reward that way. If I press the stop button, it just won't care. So yeah, you run the program and it starts up and it presses the stop button because, well, that's the easiest way to get the same reward. Why would it make you a cup of tea when it can just press the stop button and be done with it? And this is very not ideal. Like, you don't want this to happen. It's not something you want to deploy to your customers, obviously. And yeah, this just keeps going on. There's not many like easy ways of solving this. People are thinking of making the robot lazy so that maybe it doesn't like care about things that much. But the issue is that it being lazy also opens up a bunch of more loopholes, because it sort of means that it's lazy, and it just feels like, oh yeah, I guess I'll just rewrite my source code so I'm even lazier. Why can't I do that? I'm already lazy. I'll just change my objective, because that'll make things much easier, right? So one last attempt you might consider is just to like have the reward of the stop button be a smidge lower than the reward of making you a cup of tea. And you try that out, but that doesn't work either. And it still depends on what sort of model we're talking about, like what sort of general intelligence we're defining here. But it's, we're thinking about it in a very extreme form, just to make the thought experiment simpler to work with. And the fact that, this isn't super realistic, but at a higher scale, it's still possible. ChatGPT doing things despite it not, like you have jailbreaks where you can tell it to do something it's not supposed to do just because of the fact that it was trained to work with humans and things. So yeah, we can think about that, but yeah, lowering the reward of the stop button still doesn't do anything because it would be missing out on a reward, that extra smidge of reward, bringing you that cup of tea. So obviously it depends how extreme this AGI is, but just very complex to define, really. And lastly, let's say you're a bit, this might sound like the ideal solution. It might sound like it's super stupid, just like putting the stop button on the robot. And in a way it is, but the issue is once you do take it off, it gives you this false sense of control. Because once the robot believes that it doesn't actually have control over the stop button, then it's going to act how it's supposed to, and you'll be happy. But it's not acting the way it's supposed to because you've trained it that way. It's acting that way because it doesn't want you to press the stop button. So sure, it might be acting normally while you're in training and you're testing it out, but once you've actually put it into deployment and it realizes, oh wait, there is no stop button, it just does whatever it likes. An interesting, even more extreme analogy was thinking about people like actually trusting a very super sentient AI and letting it out onto the internet, and it behaves normal for a very long time because it doesn't really care about time. And then after a while, it starts to realize that, well, it's actually in reality, like it notices, wow, there's so many websites, there's so many cryptocurrencies, and it understands that it is real. And then it's like, oh wait, so there isn't a stop button. So I guess I could do whatever I want to. Because, you have the testing environment, and the testing environment might act normal, but then once it verifies that it's out of the testing environment, so maybe, humanity has been working fine with AI for 100 years, and then it realizes, oh wait, this signal from outer space, those are aliens. They could not simulate that in a simulation. I guess I'm probably in reality. I'll start copying my source code over to another server so they don't have control of me. Sure, they might be tapping my feed, but I'm still pretty sure I could get around that. So, you know, food for thought. There's a few other combinations that you could think about. So yeah, misalignment is a twofold issue, which is pretty annoying because, you know, I've already explained this to you, and now I'm actually going to be explaining that it's happening at two sort of different alignment stages, where you have the base optimizer and the model, the mesa optimizer, or sub-optimizer, you could say. And the best way to compare this is to like evolution, right? Evolution is that really top, you know, this guy, right, for us. And his objective is for our species to, you know, be as much as possible, like, you know, our genes are all around the place. So it tries to project it, it succeeds in projecting its objective at the base optimizer, and you could consider that as, you know, natural selection, or that idea of just the fact that if you have more of your species than another species, then your species is probably better. And then that objective has to be aligned with our objective. But you'll find that it's not. You know, humans still make art for well, we have our reasons, but it's almost like a mesa objective. It's just, you know, we have zoos, we have all of these random things, like we have famous people, we have social media, and people are like scrolling and things, and it just doesn't really seem like it aligns with with evolution's own objective. And the cool thing is, I mean, the annoying thing is that it's real. You know, inner misalignment has been tested out in like simulations. So, do you think you can like tell the difference between training and deployment areas here? It's probably people up front. I don't know if people at the back can see that. No. It's a bit of a game to spot the difference, but it sort of goes pretty wrong. And in the training, well, now it's closer, but you can see that there's a lot less keys than there is in the deployment. And in this game that they simulated, this is a study basically done on misalignment called goal misgeneralization in deep reinforcement learning. So yeah, that's that. But they did this study, and the game was that the agent had to unlock all of these chests and doors with the keys, and he had to go around and getting the keys and opening the chests. And in the training, he actually, the agent misrepresented his terminal goals, or the terminal goals of the game, with the instrumental goals. So terminal goals being like what you want to do just because, you know, you win the game because of it. So terminal goal should have been to open chests, and the instrumental goal would have been getting keys to open chests. However, in deployment, they found that it actually, you know, it did the opposite. Because keys were so scarce in training, it considered then the terminal goal in deployment, and it started collecting keys all around the place, and it actually missed one chest. So here's a video. I stole this off a YouTube video, so this guy's shoulder might come up, but here's the agent playing, like collecting way more keys than necessary, getting sort of confused. He gets a few chests there, but yeah, he has like way too many keys, and now he just ignores the last chest. He tries to collect the keys in his own inventory. So he's just the objective, his own, the agent's terminal and instrumental goals have been completely misaligned. And that's not good. It's a very small example, but you were looking at this game and spot the difference. Here we go, right? It was done intentionally, but the point is, once we start dealing with a super intelligent AGI who's actually smarter than us, how are we supposed to spot these differences where maybe only it could actually tell the difference? It just gets very confusing. And finally, this is probably one of the most interesting news that has been muffled, in my opinion, by the rise of ChatGPT. This is an example of real misalignment. Like, just it's absolutely crazy because it had to do with the game of Go, and it was an AI called Catago, which it was thought to be superhuman, I guess. Well, it wasn't human. It was just unbeatable, right? Not even a superhuman could beat it. It beat the world champions, and you couldn't beat it. A bit like you would consider a chess AI. You can't beat a chess AI, right? It's beaten all the tops as long as it's like the Go AI of Stockfish. If you've heard of that, that's the chess AI nowadays. But yeah, so a little bit of a history lesson. In 2016, AlphaGo by DeepMind, beat the world champion Lisa Doll. It was like 4-1, which was crazy. It was like an advancement in neural networks. They realized that these things actually have good potential. And from then on, people thought, it's done. This was 2016. This happened, this category issue happened this year in January. So, that's been 7 years. I don't understand that, but now that we get to it, an amateur beat this AI 14-1 using a strategy or a different approach to the game where they played sort of like at a larger scale. I don't know if you can see that, but the point is usually these games end up a bit differently where you have more tinier games, you could say, but obviously these black covers just such a huge territory in Go, and white has been completely confused because that's category, right? And yeah, this amateur was able to beat it because they found out that the AI doesn't actually understand the rules of Go. They found that it was good at playing the game well against people or other bots, but then when they tried out this approach where they played at such a big scale, you could say, it just was confused and it started blundering and it just didn't understand the game. I saw a video where this guy was showing off this approach, and at one point he just played this one move and the AI was like, oh wait, I'm doing this all wrong, and it just like the estimate of its score just like jumped this huge amount. It was like, yeah, I'm definitely not winning this. It just realized at one point. So yeah, this was quite some interesting news, and there's a cool video by Carl Hill on YouTube about it, so you should check that out. Well, yeah, learning about misalignment has definitely brought me to agree with this guy, Jeff Hawkins, who wrote a book called On Intelligence, which I read. And it's sort of that, like, I don't think using so much compute and hardware and all of these things that people think, just make the model bigger, is going to produce actual sentience. I don't think, I've heard other people say it obviously, but I don't think the general public knows that you can just, I don't think that transformers are the future of general intelligence. And, well, I did a bit of maths with my friend at school, just out of interest, and we know that ChatGPT has absorbed 500 gigabytes of textual data, which is absolutely crazy, and just being like super optimistic, right, over-calculating as much as possible to be sure, doing the math on humans at 150 words per minute, optimistically 8 hours a day we're conversing maybe, for 365 days a year, 72 years is the average lifespan, and let's say each character is a byte, which makes the average word length 5 bytes. Well, from this, we actually only get 9 gigabytes of textual data over 72 years. So that's just like, 50 times more. ChatGPT has consumed 50 times more data than a human in their entire life. And it's still, you can still persuade it that 2 + 2 = 5, which is It's just so crazy, I think. And not to mention that, like, I can persuaded that 2 + 2 equals 5, and I'm delivering this presentation here at 15. So, divide 9 gigabytes by 5. So, even being like super optimistic, I've only consumed 2 gigabytes of data, in a way. And ChatGPT is still just this dumb sort of thing that has 100 billion parameters, and we have 100 billion neurons, and it runs every token is a whole feed forward. It fires every single neuron in its neural network, every single token, and it generates like 10 tokens a second, while a human neuron fires every once every 2 seconds, or once every 10 seconds, or something like that. But yeah, so anyway, thank you for listening, and I hope this presentation brings some awareness to you of AI safety, and maybe taught you about some of the technical details of AI and deep learning and backpropagation, and maybe like why ChatGPT sometimes doesn't seem to grasp the wider picture of whatever you're trying to explain to it. And I'd like to leave you with this quote by Alicia Yudkowsky, American artificial intelligence safety researcher, which is, by far, the greatest danger of artificial intelligence is that people conclude too early that they understand it. That's it.